Welcome to The Explainer. I am so excited to dive into this with you today. Okay, let's talk about something that literally forms the foundation of our modern world. Most of us, we just walk right past it every single day. We see gray sludge that hardens into a sidewalk and we really don't give it a second thought. But the truth? The science behind modern concrete is an absolute high-tech, fiercely engineered marvel. Today, we're exploring the surprising evolution of concrete together. We'll dive into the chemistry, the engineering, and the radical innovations that are completely reshaping how we build. But right before we get into the cool high-tech solutions, we kind of need to understand the scale of the problem we're dealing with. Just look at this staggering statistic. More than 7% of the entire world's carbon dioxide emissions come directly from the production of Portland cement. 7%! That is a massive environmental footprint. And the reason? Well, it's the sheer heat required to make cement. We're talking about burning fossil fuels at a blistering 1,450 degrees Celsius. It makes the concrete industry one of the absolute most energy-intensive on the planet. And yet, we can't just stop using it. As Emma Ramaya, a former director of the Structural Engineering Research Center, so perfectly put it in our source text, we are in the age of concrete. I mean, that quote brilliantly hits the nail on the head regarding the tension we're facing, right? Concrete's versatility, how easily it can be molded, its sheer raw strength, it makes it the absolute bedrock of global infrastructure. We rely on it completely. So that means we have to find ways to make it better, stronger, and significantly greener. But to do that, we first need to completely rethink what this material actually is.
Section 1. The concrete misconception.
Okay, so there's this incredibly old, oversimplified saying in the construction world. It goes, broken stone, sand, and cement make good concrete. But here's the catch. Those exact same ingredients can also make terribly bad concrete. The crucial takeaway here is that just tossing these basic materials together into a mixer isn't enough anymore. The difference between a bridge that stands strong for centuries and a pavement that just crumbles after a decade, it all comes down to strict quality control and highly advanced chemical proportioning. For decades, the whole industry was pretty much hyper-focused on just one metric, compressive strength. Just asking, how much weight can this thing hold? But as we'll see, that tunnel vision led us straight into our next major challenge.
Section 2. The durability dilemma.
Engineers eventually hit a wall. They realized that high strength, on its own, simply doesn't prevent a structure from failing when it's placed in harsh environments. And that brings us to HPC, or high-performance concrete. Take a look at this really complex matrix of properties on the screen. Modern engineering demands so much more than just brute strength. It needs dimensional stability, so the concrete doesn't shrink and crack over time. It needs incredibly low permeability, so water literally can't get inside. And it needs serious resistance to chemical attacks. If we ignore these factors, well, we end up with catastrophic failures, whether that's from internal chemical reactions or just the daily cycle of freezing and thawing. This comparison brilliantly illustrates the demanding extremes our modern concrete has to face. On the left, we've got the Hoover Dam. It's a massive, mind-boggling infrastructure project that requires immense volume and structural integrity just to hold back unrelenting water pressure. Then, on the right, look at those intricate, ancient stone carvings. Today, our concrete is expected to perform flawlessly on those vast, demanding scales like the dam, while at the exact same time maintaining the precise structural stability that defies the elements over centuries, much like those ancient monuments. But here is the real villain of our story today, the 28% porosity problem. See, traditional hydrated cement paste has an inherent natural porosity of about 28%. So I want you to think of normal concrete not as a solid, impenetrable rock, but actually more like a microscopic sponge. Those tiny little gel and capillary pores, they let in water, they let in chlorides, and they let in sulfates. When that trapped water freezes and expands, or when those aggressive chemicals attack the steel reinforcement buried inside, the concrete literally destroys itself from the inside out. So how do we fix a microscopic sponge? Simple. We re-engineer the entire recipe at a molecular level. Section 3. Ultra-high-strength solutions. Let's compare some traditional mixes to what's known as reactive powder concrete, or RPC. Over on the left, we have an RPC mix yielding 200 megapascals of strength. That alone is a massive measure of pressure. But on the right, a totally mind-boggling 800 megapascals. To put that into perspective for you, normal, everyday concrete is usually hovering around 30 to 50 megapascals. No way, right? How do they even do that? Well, they actually remove the traditional sand and coarse aggregates entirely, scratch the old recipe. Instead, they use ground quartz that is as fine as 4 microns, silica fume, highly advanced superplasticizers, and these tiny steel fibers. By densely packing these ultra-fine particles together, they almost completely eliminate those microscopic voids we just talked about. And let's move to another astonishing breakthrough: compact reinforced composites, or CRC. By packing in 20 to 30% silica fume by weight of the cement, alongside superfine steel fibers into a really dense matrix, CRC achieves a flexural strength of up to 260 megapascals. Guys, this is a material that is literally as strong as structural steel, but with the massive distinct advantage that it can actually be molded and fabricated right there on the construction site. It fundamentally pushes the boundaries of architectural design. But having incredible strength is really only part of the equation. We still have to physically get this thick material into complex molds and do it safely and efficiently. Section 4. Revolutionary New Mixes. Originally developed over in Japan to offset a severe shortage of skilled labor, self-compacting concrete, or SCC, has totally been called the most revolutionary development in concrete construction in decades. Normally, when you pour concrete, you have to use these loud, heavy mechanical vibrators just to force the trapped air bubbles out. But SCC, it is engineered with highly specialized superplasticizers, so it flows like a thick liquid, perfectly into every single corner of a mold, entirely under its own weight. Because of this, we get significantly faster construction, drastically reduced noise levels, and a vastly safer working environment for the crew. A real game changer. Okay, but what about fixing that 28% porosity problem, that microscopic sponge we talked about earlier? Enter polymer composites. This slide compares two really fascinating methods. First up, polymer impregnated concrete, or PIC. Here, precast concrete is actually dried in an oven. The air inside its pores is completely vacuumed out, and a liquid plastic monomer, like methyl methacrylate, is infused deep into the stone. It's then polymerized using heat or radiation. Pretty wild, right? Now contrast that with polymer cement concrete, or PCC. In this method, the plastic monomer is just mixed directly into the wet cement from the very start. Both of these methods effectively plug up the sponge, completely sealing and protecting the concrete from within. These highly impermeable mixes, combined with clever techniques like ferro-cement, are solving critical problems in some of our absolute harshest environments. Just look at these applications, including an actual marine boat. Ferrocement uses closely spaced wire meshes that are impregnated with a very rich cement mortar. It creates incredibly thin, lightweight, yet highly durable structures that can actually flex without cracking. That makes it totally perfect for highly corrosive environments like sewage disposal works or floating right there in the salty ocean water. Now, all of these advancements are absolutely incredible for durability and strength, but we still have to address that massive 7% global carbon footprint from earlier, so let's pivot to the ultimate resolution. Section 5. Sustainable Zero Cement Futures. One of the absolute best, most immediate ways we are dropping emissions is through something called high-volume fly ash concrete, or HVFC. This technique takes up to 57% of ordinary Portland cement and replaces it with industrial byproducts, specifically things like fly ash, which is just waste from power generation. By doing this, we dramatically lower the environmental impact. In fact, a massive concrete foundation for a beautiful Hindu temple in Hawaii was poured using this exact 57% replacement mix. It was explicitly designed to last for 1,000 years, all while staying incredibly sustainable. But what if we could get rid of the Portland cement entirely? I mean, completely zero it out. Look at this brilliant twist: geopolymer concrete. Instead of traditional cement, this uses an inorganic aluminosilicate polymer synthesized primarily from fly ash and an alkaline solution. There is literally zero ordinary cement in this mix. None. The geopolymer gel binds the aggregates together through a really fast chemical reaction, curing to a super high-strength bond in just 24 to 48 hours. It is an absolute paradigm shift for the whole industry. Which leaves us with this final provocative thought. If we can manipulate microscopic gel structures, if we can eliminate porosity with liquid plastics, and synthesize ultra-strong infrastructure without a single ounce of traditional carbon-heavy cement, what will the cities of tomorrow look like? We are no longer just pouring gray sludge, my friends. We are engineering the very fabric of our future at the molecular level. Thank you so much for joining me on this explainer today. Keep learning, keep questioning, and I will see you next time.